Okay, Tony, I could go anytime.
Okay, good. So, first of all, I think we owe John a round of applause even before he starts, because for him it's 3 o'clock in the morning and he was willing to do this and be here with us. So let's do that. Needless to say, many of us know John, and for those who do not, we're very, very fortunate to have one of the world's best to talk to us about the neutrino sector. So this is really, really a gift, and it's wonderful that Marek has been able to work around the fact that there was no way, oddly enough, for John to get here. The flights were all packed. So, John, thank you for being here. Also for your patience in trying to get here in person. And on that note, I'll turn it over to you. I will let you know. I'll flash in the camera the 5 minute mark. You have 45 minutes, and then we'll take a break, and then there'll be another 45 minutes after that. So, and so basically, in the second 45 minutes, if we could allow about 5 minutes for some in this 45 minutes, if we could allow a little bit of time at the end for some questions, and then again in the second session. Make sense? Okay, good. Thanks, John. Go ahead.
Dzień dobry. Chciałbym tambić osobiście. So many of you are interested in supernovae, and you think you know what you're getting into. You think all you have to do is look up at the sky. Just a minute. And find a place where the astronomers have already drawn an arrow, and then wait, and great things happen. And that's true, but the problem is, once we zoom in on that, we get a lot more than we bargained for. We get what is technically known as a ball of snakes, a very, very complicated problem. So supernovae have been known for millennia, but now we have some idea of what they actually are. Here's an example of a recent supernova in a nearby galaxy, a core collapse supernova. And this one was discovered here, as you can see on the left, by basically a difference image that we see the galaxy before and after, and you see the supernova starting to emerge. Eventually, the supernova will become comparably bright to the entire galaxy itself. So that's what the optical display of a supernova looks like. What do we see in detail? What we see in detail is both the light curve, which is the fluxes of different bands of light versus time, and the spectrum, which is the zoomed in version of that, with higher frequency resolution. And this detailed information allows us to understand quite a bit about what's happening with the explosion. So these two observables, the light curve, basically the time profile of the signal, and then the spectrum, the energy profile of the signal, these are the key things that are important in the electromagnetic spectrum. They'll also be very important in the neutrino spectrum. So the key characteristics of supernovae are they're super rare, maybe 1 per century per galaxy, depending on details. We know that they're very, very energetic. Even a core collapse supernova is something like 10 to the 49 ergs in the electromagnetic spectrum. They're transient. They last, weeks to months to years, depending on how low in flux you can go. They're conveniently observable in the optical. If you look closely at the bottom figure, it looks like it's peaking in the UV, but that's because they plotted F lambda instead of lambda F lambda. It really peaks more in the optical. And they're resolvable, meaning that they eventually become macroscopic so that we can see across their surfaces. And that most famously is seen in things like supernova remnants, which is the final state. That's all great. These are the observed facts, but it leaves something really important unknown, which is what actually are they? And as you know, there's more than one kind of supernova, and it's really a remarkable fact that nature has at least two ways, probably well more than two ways, to make things that look rather similar to each other that are extremely, well, extreme. So something that can basically temporarily outshine its entire galaxy in the optical. It's amazing that there's more than one way to do that. And it's our job to figure out what those ways are. So in this first lecture, which is intended primarily for students and postdocs who probably come from like the gravitational wave side or the optical side and are interested in neutrinos, that's what we're going to cover today. We're going to introduce neutrinos and then talk about how they're produced, how they propagate, and how they're detected. And in the next lecture, we'll talk about some of the research frontiers. So here's a very basic picture of how we understand supernovae. Let's just start from low mass and high mass stars. Low mass stars can eventually evolve and form a white dwarf, as shown in the diagram here. High mass stars can eventually evolve into a supergiant and then eventually into a supernova that can end either in a neutron star or a black hole. Now, I want to illustrate something. This is, literally straight out of the encyclopedia, and it seems to say that we understand quite a bit, and we do, but there's a lot we don't know. So let's focus just for a minute on the thing that's not the topic of this talk, which is thermonuclear supernovae. And I just want to point out something, that for 1A supernovae, we use them to measure cosmological distances. In fact, people won a Nobel Prize for that. But incredibly, we still have no idea what a thermonuclear or type 1A supernova actually is. It could be a white dwarf that accretes material from a massive companion, like a ordinary star, or it could be the merger of two white dwarfs. And it's incredible to me that even though thousands and thousands of supernovae have been observed and type 1As are used as standard candles in cosmology, there's still this fork in the road that we don't know which thing is happening. And so on the massive star side, I think we should have an open mind that maybe we know less than we think we know. So for massive stars, these are stars greater than about 8 solar masses. They live fast and die young. They're pretty rare. They're extremely luminous. They live at most about 30 million years. And these lead to core collapse, or typically type 2, technically also type 1b and 1c supernovae. And it's these core collapse supernovae that are the focus of these talks. And this neat picture from the encyclopedia basically says, oh, a massive star evolves, somehow it blows up, and it either makes a neutron star or a black hole. And that's a very pat story. But I think we have to have an open mind that even this story may be much more complex than we actually think. And maybe not all core collapse supernovae are the same as each other. Even just the ones that make neutron stars or just the ones that make black holes, there might still be a lot more variety among them than this simple picture illustrates. And how are we going to find that out? We have to have more and better observables coupled with more and better theory to figure out the underlying story. So one of the earliest versions of what happens in a core collapse supernova comes from Gamow and Schoenberg in 1941. And they had amazing ideas, mostly correct. 2 out of 3 is not bad. They had the idea that a massive star somehow collapses on the inside. They thought it forms a white dwarf. That's not quite true, but it was a good guess. And they thought that the core collapse would lead to a burst of neutrinos, which was pretty amazing for a 1941 paper. And they thought that some magic would happen and the envelope would be heated and the envelope would be pushed out and would expand and make the optical supernova. These were not the only people nosing around in this direction. Bada and Zwicky, Oppenheimer and Volkov, everybody was getting some of the pieces, but nobody had quite all of them. But that emerged over time. A more modern understanding is that by some miracle, the core collapses and forms either a neutron star or a black hole, like we just saw. This always emits neutrinos, even if it forms a black hole. We'll talk about that more later. And it usually emits light. So if it's a successful supernova that makes a neutron star, we think the shock ejects the envelope and it makes an optical display. If the shock fails and everything collapses back down to a black hole, it's possible that there's no electromagnetic display at all. And we'll come back to that. And a core collapse supernova might emit gravitational waves. If it's perfectly spherically symmetric, it does not. But there's a lot of reason to think that core collapse supernovae are not spherically symmetric. And this is one of the things we want to find out both observationally and from theoretical modeling. So here's a homework problem for the students, postdocs who are new to neutrinos. We're not going to work through this now, but I encourage you to think about it later. Obviously, you probably have heard the answer already, or you can easily find it. That's not the point. The point is learning how to calculate it yourself. It's actually quite easy if you approximate like crazy. And if you're not familiar with calculating things in approximate ways, what I encourage you to do is make so many approximations. Just keep making more and more approximations until the problem crumbles to dust in your hands, and then undo one of the approximations so that you still have a problem to work with, and that's about the right level of approximation. And what you could do is figure out how much energy must be emitted by these neutrinos. So we also have observational data, and you've all heard of supernova 1987A, but I want to illustrate why it's so important. So 87A, first of all, showed that a massive star, that's literally where the arrow points on the left, you can see the individual star that had a name. An individual massive star eventually becomes what astronomers call a type 2 supernova. That was proven for the first time with 87A. Also, it was proven for the first time that the supernova is accompanied, actually preceded by, an energetic burst of neutrinos. Here's a scatter plot of about 20 neutrinos observed in the Kamioka and IMB detectors. It's a scatter plot of their energies, low tens of MeV, emitted over about 10 seconds. And third, it connects it to the theoretical idea that core collapse makes a proto-neutron star and neutrinos, and then somehow, by a miracle, the shock ejects the envelope and you get the optical display. So this is why we think that basic picture is correct. However, it leaves a lot unanswered, and it's our job to figure those things out. So why are supernovae so interesting? I mean, obviously, I probably don't have to convince you. You literally are having a conference called Supernova 2025 GW. But let's review what we want to find out. We want to find out what is happening that explains all of the observations. And, what do supernovae reveal? For example, supernovae can be used as distance indicators. It's less easy with core collapse supernovae, but it is possible, and it could get better. Supernovae destroy some things and they make other things. Some of the things they make are obviously neutron stars and black holes, but they also make a lot of the chemical elements. They also make feedback that distorts galaxies. They seem to make cosmic rays, and they definitely make neutrinos. And we also want to know, how can we use these extreme environments to probe physics beyond the laboratory? So, for example, to probe neutrino properties that we just couldn't test in the laboratory experiment. And also simply because explosions are cool. I think many of us got into this field because probably had a little too much interest in explosions, and there's nothing wrong with that. So how do we want to find supernovae? Well, we want to find them across the entire electromagnetic spectrum. We want to find them in neutrinos and gravitational waves, ideally with broad frequency or energy coverage. And we want to observe them sort of before, during, and after the explosions. And why? The reason it goes back to that ball of snakes I showed on the title page. Supernovae are incredibly complicated, and this is the only way we have that could possibly figure out all the things we want to know. So what specifically do we hope to learn? Focusing here more on the core collapse side and the neutrino side, these are just some of the questions. We'd like to know how much energy is emitted in neutrinos and how is that divided among the neutrino flavors, the spectra? What do we learn about neutrinos or other particles? On the astrophysical side, we'd like to understand the actual supernova explosion mechanism. How is the shock successfully launched, for example? What chemical elements are produced, et cetera, et cetera. These are great questions, and this is only a partial list. This is, on one hand, very difficult. On the other hand, answering these questions would address questions that have been around for decades and could likely lead to enormous discoveries. So there are a lot of obstacles, but there are a lot of ways forward. One of the obstacles is that supernova rates are too low or signals are too hard to detect. Well, that's easy. We just build more sensitive detectors. We can't make the supernova closer, but we can make the detectors reach farther. They're really, really complicated. Well, that's why our field has invented multi-messenger astronomy, and that's why we're trying to use that to couple different kinds of observations together in a theoretical framework. And these neutrino and gravitational wave signatures in particular are very, very faint. And they will always be hard to detect. And that's okay, because they greatly leverage what can be extremely precise electromagnetic observations. So neutrino and gravitational wave observations will never be at the level of precision of the electromagnetic observations. But they measure different things, and they don't have to be as precise to be incredibly powerful. Just to give one example, if we had super powerful neutrino detectors, and well, we do have them, and there's a Milky Way supernova, if there's a burst of neutrinos, we know that there was a core collapse supernova. If we don't see a burst of neutrinos, it was probably a 1A supernova. So that's an example of how even not having a huge amount of data can have a very dispositive outcome. So I'd like to introduce neutrinos for people who are new to them. And like I said, I'm assuming that a lot of the audience is from the gravitational wave side or the electromagnetic side. And I'm told that the purpose of these lectures is to help, in particular, introduce students and postdocs in these areas to the broader topics of the conference. So let's start with what neutrinos are. So as shown on the left here, neutrinos are, part of the sort of periodic table of elementary particles. And I want you to notice that just above the electron there on the left, there's an electron neutrino. Just above the muon, there's a muon neutrino, and same with the tau. Those are partners, and neutrinos, I'll talk more about that in a second, but neutrinos are neutral partners of the charged leptons. Because they're neutral, they could be their own antiparticles, which is not true for electrons because of charge. Neutrinos in the standard model are nominally massless, but we now know they have tiny masses. And neutrinos, if they're massless, have only weak interactions. If they have masses, they also have some small gravitational interactions. But they don't feel the strong force and they don't feel the electromagnetic force. And that makes them, their weakness gives them power. So as shown in this Feynman diagram on the right, an electron neutrino that comes in here can couple through a W and change a neutron into a proton, emitting an electron in the process. Similarly, a muon neutrino could come in and make a muon going out. And same with a new tau coming in could make a tauon going out. But because we're interested in the MeV energies of supernova neutrinos, it's important to understand that the reactions with nu mu and nu tau cannot proceed because the muon mass and the tau mass are much too large for these neutrino energies to produce. So the only charge current interactions we can have for supernova neutrinos involve electron neutrinos and, of course, electron antineutrinos. At much higher energies, like for IceCube or whatever, it's possible to see charge current interactions of all three flavors. All of the flavors can also participate in what's called neutral current interactions, where they talk to matter through a Z boson. And this is possible because there's no threshold in this reaction. It's just elastic scattering. And besides the reaction shown here, this can happen with electron targets or other targets as well. Now, cross sections for these neutrino interactions are extremely small, and we'll come back to that. So shortly after the discovery of neutrinos as messengers, shockingly soon after their discovery in 1956, people started talking about using them as astronomical measurements. I mean, they had just concluded a decades-long quest to detect neutrinos at all, and they had, just barely. And that was their first thought is, hey, we did it, we detected neutrinos. Their second thought is, I wonder if we can do astronomy with these. That kind of bold thinking is really exciting. So wherever matter is hot and dense, neutrinos are made. Wherever the chemical elements are produced, neutrinos are made. And wherever hadrons are accelerated, neutrinos are made. That's why people were excited about using neutrinos for astronomy, because wherever these processes occur and neutrinos are made, those neutrinos cannot be hidden. So if you can detect those neutrinos, you can reveal these processes, even if those processes are hidden from electromagnetic observations. They can't be hidden from neutrinos. So neutrinos let us see the deep insides of sources and all of these other things. So for example, neutrinos let us see the core of the sun. These and other reasons make them basically ideal astronomical messengers. The only problem is that they're hard to detect. But we can fix that problem by making bigger, more sensitive detectors. So because of those efforts, neutrino astronomy is now a real discipline. And not only have we seen neutrinos from the sun and one supernova 1987A, we've seen neutrinos from our own, produced in our own atmosphere. And we have IceCube and now KM3Net have detected neutrinos from somewhere out in the universe, some kinds of extragalactic high energy sources. So how are the supernova neutrinos produced? In this diagram on the left, the basic idea is that once the core of a massive star has evolved to be basically pure iron, it is unstable to electron capture and nuclear dissociation. And if that happens and the core starts to collapse, let's follow the core just for a minute. The core of the star might be thousands of kilometers in size, quite dense, but not infinitely dense. And if that starts to collapse, how far can it go? Well, the furthest we know of that it can go and still be a visible object is to make a neutron star, which has super high density, nearly nuclear density, and a radius of about 10 kilometers. Could even collapse further into a black hole, which is not directly visible. And then what happens with the rest of the star? What we think happens is that when it first collapses to the protoneutron star, which means the early phase of the neutron star where it's more hot and has not yet shed all of its energy, and that can go further down to a neutron star or a black hole, we think that collapse to a protoneutron star triggers an outgoing shock. And also that the outgoing neutrinos from the protoneutron star could even power that shock or heat that shock. And that by some miracle, that shock would push off, maybe 10, 20, 30 solar masses of material of the envelope and push it out very, very far, making it basically unbound and liberating all of the electromagnetic energy that is bottled up inside of the star itself. That's why there's a tremendous optical display, because, it's like taking a baked potato and it's very, very hot on the inside, but you can't really get to it, and ripping it open, all of the heat can get out at once. That's basically what's happening with the envelope of the star. Now, what you learned in school is that all the neutrinos come from what's called the neutronization process, that electrons capture on protons and make electron neutrinos and neutrons. And that's true. It does happen. It turns out, though, that this is just only subdominant. The really interesting thing is, this goes back to the point I made a few minutes ago, is wherever matter is hot and dense, neutrinos are made. So one thing that can happen, and I'm going to grossly simplify this, is you can have an electron and positron in the very high temperatures and densities of the core. You can have a real electron and a real positron reach each other, annihilate to a gamma ray, and go back to electrons and positrons. And again, and again, and again, and again, and again. How often is set by the electromagnetic cross-section. But every once in a long, long while, electron and positron can go to a Z, which can go to a neutrino and an antineutrino. And then those neutrinos have a chance to escape. So the outcome of E plus E minus going to nu bar is rare, but if you try a semi-infinite number of times, you will eventually get it. And when you do get it, those neutrinos can leave. And that's not the only way to produce neutrinos. Another way is nucleon, Bremsstrahlung. And the total energy emitted in neutrinos is about 3 times 10 to the 53 erg. To put that in context, that's considerably larger than the energy radiated by the sun in its entire lifetime. In fact, this is about 10% of the MC squared of an entire solar mass or more. It's pretty amazing. This is almost like, supervillain territory. Let's take more than one solar mass of material and let's get almost MC squared out of it. That's almost like you took a solar mass of matter and a solar mass of antimatter and put them together. And why is it that only neutrinos are emitted? Well, everything's emitted, but why is it neutrinos carry almost all of the energy? Because they're the only ones that can get out. When you look at the massive star, the surface of the massive star, the photons you see are only coming from the thinnest shell at the surface, and definitely not from the deep interior, and definitely not from the neutron star itself. Photons just can't get out. And gravitational radiation is a minor part of the energy emission at best. Nothing else can get out. Only neutrinos have an opportunity to possibly escape. So they're the ones that have to carry away this energy. There has to be a gravitational binding energy release when you take something that's thousands of kilometers and you shrink it down to tens of kilometers. So here's another homework problem for you to think about the protoneutron star. It's fun to estimate what's its mass density. Well, you have something like 1 or 1.5 or maybe 2 solar masses worth of material in a radius of about 10 kilometers. And what should that tell you about the number density and the mass density? They're enormous. And what does it tell you about the column density? The column density, what I mean is the number density times the radius. And what you'll find is that column density is absolutely enormous. And it's bigger than the inverse of the neutrino cross-section. So the column density is measured in per centimeter squared. And the neutrino cross-section is measured in centimeters squared. And so if you multiply those two things, you get the expected number of interactions. And what you'll find is that even the neutrinos would be interacting in the protoneutron star. So what that means is, while neutrinos can escape from the protoneutron star, even they are trapped. How long? Well, they're trapped for several seconds. And in this paper, we show how to make some quick estimates that the average energy in the core of the protoneutron star, the neutrinos have like 100 MeV, but by the time they reach the surface, it's more like 10 MeV, and that the diffusion should happen over several seconds. So quite a lot can be figured out just by basic estimates. But it's not enough. We have to really couple this with sophisticated numerical models. So one of the things that happens is, because the neutrinos diffuse through the core, they decouple with a thermal spectrum that is characteristic of the surface of last scattering that they experience. Those thermal spectra are shown here in this example plot on the left. And I want you to notice that the so-called nu X neutrinos, that's nu mu, nu tau, and their antiparticles, have a hotter spectrum than the other flavors. And that goes back to the point that they don't have charge current interactions. They're not kinematically available. They only have neutral current interactions. So because they have a smaller cross-section, they decouple deeper inside the star where the star is hotter. And there's some slight differences between nu-E and nu-E bar. Nu-E interacts the most compared to nu-E bar, so nu-E decouples the farthest out and has the lowest average energy. The different phases of the collapse are shown on the right. One thing I want to highlight is there's a pre-supernova neutrino emission signal from the star itself. That can happen in like days or hours before the actual supernova. It could be an early warning system. It's very, very hard to detect. One of the very exciting papers about that was written about 20 years ago by Odravolik, Kuchera, and Mizyazik. I think I got the three names correct. And there are now active searches for those neutrinos as an early warning of a core collapse. The core collapse itself has several phases shown in this diagram. I'm not really going to be able to get into the details in this introductory lecture, but it is complicated, and I want you to know it's complicated, even though throughout I'm making a lot of simplifications. I'm doing that so everybody has a simple framework in their head to be able to fill in the details from the successive talks, the ones that come after this one. So how do neutrinos get to us? Well, one cool thing, since they barely interact, is they just travel freely through the universe and they don't worry about anything. Now, that's almost true. And one thing you know about, and we talked about this already, is an electron neutrino is the one that couples to an electron, and a muon neutrino is the one that couples to a muon, etc. But you probably also know that neutrinos have some masses, very, very tiny, but we know that they have some differences between them. And these mass states and these flavor states are not identical. So it makes no sense to talk about the mass of the electron neutrino. It's really a superposition of different mass states. And there's a transformation between these with a unitary matrix. And we work in the ultra-relativistic limit, where the neutrino energies are huge compared to the masses. And even in vacuum, this leads to the possibility that you start with a bunch of electron neutrinos, and then later you have some probability to have other flavors, nu mu or nu tau. So neutrinos can change flavor even in vacuum. But there's more. In matter, neutrinos can also couple to matter through these diagrams on the left, and this leads to a neutrino index of refraction. And you know that another way to interpret the photon index of refraction in matter is it's like a photon effective mass. It's like the photon travels at less than the speed of light in vacuum. It travels at c/n. And in fact, so this, the MSW effect, Mikheyev-Smirnov-Wolfenstein effect, can change how neutrinos oscillate in matter. But wait, there's more. The neutrino densities in the protoneutron star are so high that when neutrinos travel through other neutrinos, that also affects how they mix. And what this leads to is a very complicated situation that is, to this day, unsolved. People have solved the vacuum neutrino mixing case. That's great. People have solved the MSW case where neutrinos interact with electrons. That's great. But nobody has figured out how to solve how neutrinos mix in the presence of other neutrinos. And you might think that this is a problem, that we don't know, even though we know the core collapse supernova emits all flavors of neutrinos, nu e, nu mu, nu tau, and their antiparticles, we don't quite know how those flavors mix inside the supernova. One thing I don't have time to explain, but I want to emphasize, all of the mixing happens inside the supernova. I know that sounds counterintuitive, and I wish I had time to explain it, but in between the supernova and us, no further mixing occurs. And that has to do with the fact that the neutrinos have passed through a very high density of matter that polarizes them into the mass eigenstates when they leave the star. So what that means is, if you observe two supernovae, one at a nearby distance and one at a far distance, the only difference is the 1 over 4 pi r squared in the flux. What happens with the neutrino mixing is the same because it happens inside the supernova itself, not en route. So this is a big problem, the not understanding neutrino mixing, if we want to compare dated theory. But it's not a problem if we want to do it like I just said, if we want to compare one kind of data to another. Like if we get lucky to have supernova 2025 GW and, say, GX. And part of the reason it doesn't matter for some of the things we want to answer is neutrinos are such a powerful diagnostic of core collapse supernovae that it eliminates some of the uncertainties. So how are we going to detect them? There are three ways to detect supernova neutrinos. And by the way, if you ever see this diagram, you notice I didn't put any name on this diagram about who made the diagram. That's because I made it. And you'll see this diagram frequently in talks about supernovae, but it's often missing my name. Now, the three ways we can detect them is if a supernova happens in our own galaxy. This is very, very rare, about 1 per century, but we get a huge burst of neutrinos, as I'll tell you soon, maybe 10,000 neutrinos detected. That's a burst. It's also conceivable that we could detect supernovae in nearby galaxies and detect sort of one event. That's a mini burst. But the cool thing is this happens more like once a year. And there's another thing we could try to detect called the diffuse supernova neutrino background. I'll go into detail on that in the second lecture. And let me make a fake analogy. Let's imagine you have a supernova that's so far away that the expected number of detected neutrinos is 10 to the minus 6. Well, most of the time you will observe 0 events. But if you try 10 to the 6 times, eventually you're going to get 1 event. And that's basically what happens with the DSMB. So ultimately, to really fully understand supernovae, we're going to have to make observations of all 3 types. And I'll say more about that in the second lecture. So if you're a gravitational wave person, what do neutrino detectors have in common? Well, they are synoptic, which means they're just passive. They see the whole sky all the time. They don't focus, and you're just sitting around waiting for events. Some of the differences are, unfortunately for us, sensitivity falls like flux, 1 over r squared, and we're looking for discrete particle interactions. The good news is, during a supernova burst, we can ignore detector backgrounds. So here's an example of how to detect some neutrinos. Let's start with an electron antineutrino. That is a nu bar interacting with a proton, a hydrogen proton, and making a positron and a neutron. In neutrino physics, we call this a big cross-section. The positron goes out in a mostly isotropic way, and the positron carries most of the neutrino energy. And if we can detect the neutron as well, that double signature of a positron followed by a neutron tells us that it was definitely a new bar. So we have flavor identification. In neutrino detectors, we typically get the timing to the nanosecond level. But remember that the burst itself can be like 10 seconds long. Another key interaction is neutrino electron scattering. We call this a small cross-section. And these numbers look pretty similar, but I want you to notice that the scaling with energy is different. And in this case, in neutrino electron scattering, the electron is scattered very, very forward, although the energy range is more smeared. We can't tell the flavor at all. And again, the timing is very good. Some of the detectors that we have coming up are shown here. Super Kamiokande, you've heard of. It's about the size of a very large building, like one of the largest buildings on a university campus. It contains about, the inner volume contains about 32,000 cubic meters of water. Formerly, it was the purest water on Earth. And it now contains also some gadolinium, which I'll talk about in the second lecture. And that gadolinium helps them detect the neutrons. Later, it will be succeeded by Hyperkamiokande, which is roughly 10 times bigger. There's another new detector coming called Juno. If you've ever heard of Borexino or Camland, this is sort of like the super version of those. It's also gigantic in size. It's starting this year in China. And then under construction in the United States is the DUNE neutrino experiment, Deep Underground Neutrino Experiment, which is an international collaboration. And that'll be coming in several years. And that allows us to see individual particle tracks in great detail. We can come back to that. So roughly, what do we expect for a Milky Way burst? In Super Kamiokande, we expect something like 10,000 events. Now, you might think, I thought you told me at the beginning that supernova 1987A was only like 10 or 20 events. That's true, but Super Kamiokande is much, much bigger than Kamiokande. And 87A was not actually in the Milky Way proper. It was in the Large Magellanic Cloud, which is about at least 5 times farther than a typical distance in the Milky Way. So the flux difference and the detector difference account for most of what I'm talking about here. There are other reactions detected, including neutrino electron scattering. But the big thing that happens is inverse beta decay of new bars on free hydrogen protons. Interacting with the protons and neutrons in nuclei is suppressed because of nuclear threshold energies. In Juno, it's similar. The Juno is made of mineral oil, which is a clear oil. You can approximate the oil as being CH2, and that helps you understand what's going on. So a lot of things are similar to Super K, but one thing is very special to Juno, and that is the neutrinos can elastically scatter protons. So that happens in Super K too, but in Super K it's not detectable. But in Juno, elastically scattered protons could be detectable. I'll come back to that in a moment. And then in Dune, it has the possibility of having a huge number of events on nuclei directly. And one other detector I didn't mention, I'll mention briefly, is IceCube. You probably heard about this a lot of times. IceCube is incredibly big, but it has enormous backgrounds. So the way you detect a supernova in IceCube is you just look at the hit rate of all of the photomultiplier tubes over time. And what it's doing is fluctuating, 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 fluctuating. And if a supernova happens, you could get a big upward fluctuation and it could go back. And so IceCube cannot identify individual neutrino events, but they can tell the supernova happened, and they can measure its time profile pretty precisely just by the statistical increase in the noise rate. And one of the reasons it's important to have multiple neutrino detectors is in case, well, what if one of them's off? Then the other ones can be on. But also, different neutrino flavors capture, different neutrino detectors capture different neutrino flavors. And that's absolutely key to being able to reconstruct the total energy emitted in neutrinos and the details of the core. So these detectors have different sensitivities to electron antineutrinos, nu mu, nu tau, and their antiparticles. That's called nu x and nu e. Okay, so the closing message for this first talk is we can't understand core collapse supernovae without detecting their neutrinos. And in order to detect their neutrinos, we need to detect both a Milky Way. We need to detect a burst from the Milky Way. Ultimately, we need to detect these mini bursts from nearby galaxies, and we need to detect the diffuse supernova neutrino background from all the core collapses in the universe. And that's it.
Thank you very much, John, for that superb introduction to this very complex subject. Yeah, I'm going to pass off the mics. Have time for questions, Sergey?
How far the hyper-K will see the statistically significant flux of neutrino?
Okay, that's a great question. What can hyperchemiocondae do to see distant supernovae? I'll talk about this more in the second lecture, but let's start with superchemiocondae just for a second. Superchemiocondae can easily see and cannot fail to see a core collapse anywhere in the Milky Way and anywhere in the satellite galaxies of the Milky Way. So large Magellanic Cloud, small Magellanic Cloud, whatever. Super K cannot miss seeing a neutrino burst from them, even if it's optically dark. Hyper K, of course, can see, because it's, let's round off and say it's, 9 times bigger, so it can see 3 times farther. It gets to it can reach maybe to getting a couple of events from Andromeda, and I'll talk about that more in the second lecture, but unfortunately it can't reach beyond the nearest galaxy like Andromeda. To really see the nearby galaxies out at several megaparsec, we'll need something even bigger than Hyper K.
Thank you, John. Are there plans, do you know if there are plans to gallium dope hyper K2?
Yeah. Okay, so the question was, what about putting gadolinium in Hyper K? I'll say a lot more about this in the second lecture, but the short answer is, so gadolinium is already in Super K. This idea was proposed by 2 people, me, a meddling theorist, and Mark Vegans, an actual experimentalist, in 2003. And after years of R&D, it was finally figured out that it was safe for Super K. And I'll talk more about why that matters later. For hyperchemiocondae, it is not yet decided, but what I'm hoping is that the opportunity to detect the diffuse supernova neutrino background with high statistics will be so tempting, along with other physics goals, that they will make this happen. It's working great in Super K, so there's no reason it can't work great in Hyper K. It is challenging technically to build all of the systems you need to introduce and filter the gadolinium and all of that. And that requires new caverns and things like that. It's not cheap, but I know that experimentalists will follow where the data is.
Thank you. And then one more, if HyperK had been live when 2023 IXF went off, would there have been a possibility for it to see order unity events from it? It's at 8 megaparsec, so a bit too.
That's a great question. I would say it had the Poisson expectation for the number of events is less than 1, but it's not so low that you don't have a chance of getting 1. We could calculate that later, but I don't have that pre-calculated. Ultimately, for those nearby galaxies, you really needed something even bigger than Hyper K, and I'll say more later about what's needed.
It's amazing to think of what our expectations are to get. I saw you smile when John said we might have been able to see 1. That's great. Any other questions? Yes.
Hey, John. Thanks for the amazing talk. So, I have a basic doubt, I would say. So, in the beginning of the slides, you mentioned that neutrinos usually do not interact much, and not at least gravitationally and electromagnetically. So, I suppose they interact through nuclear forces. But then again, we say that the shock is powered through neutrinos. So, is the interaction between the matter in the shock and the neutrinos just due to the nuclear forces? Just the nuclear forces are enough, or is it the abundance in the number of neutrons that's the only factor that causes it to power the shock?
Yeah, that's a great question. Actually, I want to go to a different slide. Let's see. Maybe it's a little bit later. Oh, yeah. Okay. So when the neutrinos are in the protoneutron star, the very dense part in the middle, the neutrinos are interacting frequently, even through the weak interactions, because the matter is incredibly dense. The column density is very, very high. When the neutrinos leave the protoneutron star, what that means is that the probability of their interacting has gotten smaller. The column density between them and us is, the optical depth between them and us is less than 1. But what that means is the neutrinos diffuse and diffuse and diffuse in the protoneutron star until they reach the part where they have no scatterings in front of them, and then they fly free. But if they fly free, how are they going to interact with the shock? Okay, so that's your key question. Now, the answer it is, thinking from the perspective of the neutrinos, when they're in the protoneutron star, they feel, I have to interact, I have to interact, I have to interact. Once they get out of the protoneutron star, they're basically free forever. That's thinking from the perspective of the neutrinos. Thinking from the perspective of the shock, it has, a gazillion neutrinos streaming through it, and each one has a very small probability of interacting. So most of them, almost all of them, go through like nothing's happening. But there's so many of them that some of them interact. So the probability of the neutrinos getting from the outside of the protoneutron star to us is nearly 1, not exactly 1, it's like 1 minus epsilon. But even that epsilon fraction of neutrinos interacting, because the number of neutrinos is so huge, that has the potential to reheat the shock. Does that answer your question?
Yeah. Thank you, John.
And just quickly to a sort of order of magnitude that John talked about, you have several 10 to the 53 ergs of energy being emitted in neutrinos, which is the gravitational binding energy of the neutron star that's forming. And you're going to power a supernova typically of several 10 to the 51 ergs. So you just need a small fraction.
Right. So even, right, as Tony said very nicely, even if 1% of the energy were deposited, that would be plenty to power the shock.
Right.
And
Okay.
you probably need less than that.
Thanks, John.